Everything that was in the example that I did on the lecture.
Oh, okay,
yeah. Okay. It's the same as the beginning of the lecture.
Yeah.
So I have a charged particle moving with the velocity v inside of a magnetic field that's going into the board.
Bless you.
Bless somebody. This is going to experience a magnetic force. How big is that force going to be? What equation? F is equal to Q times V cross B. So it has a magnitude and a direction. What we're interested in for this is actually figuring out the direction. So to find the direction, I need to do the cross product of V and B. So to do that cross product, we use the right-hand rule. I take my fingers go in the direction of V. Fingers go this way. I bend my fingers in the direction of B. The magnetic field is going into the board, so I bend my fingers into the board.
How do you know that?
That's the rule for taking cross products.
Okay.
First variable is your fingers. Second variable is the direction that you bend.
Are we looking for the direction of B or
And
F?
we're looking for the direction of F.
Yeah, so how do you know where B was going?
We know B is going into the board because that's what all those X's are.
Oh, okay.
Those all represent the magnetic field going into the board. Yeah? Mm-hmm. What direction is my thumb pointing? Up. My thumb is pointing up. So what direction does the magnetic force go? Up. So what direction is this charge going to go? What direction is the charge going to go?
I don't know. It's like that.
Charge is going to go up. So if I come back to this charge a little bit later, it's going to have moved. Right? It still has some velocity, some initial inertia that's carrying it forward, but as it's going forward, it's going to start arcing up. Yeah? So at some point, this thing's going to change its velocity, and at some point later, it's going to look something like this. And the force drags it up, so eventually the velocity is going to actually be moving up. Okay? And all the time that it's doing this, so it feels a force that's pulling it up, so it kind of starts arcing up this way, and then it starts arcing more and more and more, so we're just capturing it over at that other side.
Can you say the rule again? It's your hand goes in this direction?
Yeah, we're going to do it again. So now I have V. Yep. I take my fingers and I put them in the direction of V. For over here, what direction is V going? Up, so I put my fingers up. I need to bend my fingers in the direction of the magnetic field. Where is the magnetic field going? Into the board. So I need to rotate my hand around so that I can bend my fingers into the board. Fingers are going up, bend my fingers into the board, my thumb is pointing in. Yep. So the force there is going in. So what direction is the charge going to start moving? To the left, So it's going to start moving kind of this over this way, right? We can capture, think about it. Thank you.
I've never seen them.
So now I've got my charge going this way. My velocity is going over there. I can do my right-hand rule again. How do I do it? What do I do? My God. People are gluttons.
What?
They've taken like 5 to 10 pieces of candy.
Oh.
Don't go too crazy. I'm not rich. Take my velocity, take my fingers pointing in the direction of velocity. What direction do I need to bend my fingers?
Down.
Into the board. So I need to rotate my hand so that I can bend them into the board. So I rotate my hand around, bend my fingers into the board. What direction is my thumb pointing?
Down.
Down. So the force is going to pull it down. So where is it going to go? Down. It's going to go down. Yep. So V is going down. What direction is the force going? How do I find it?
With your thumb, right?
With my thumb. I have my fingers go in the direction of V. V is going down. I need to bend my fingers in the direction of B, which is into the board. My thumb is pointing towards the center of the circle. So there's my force.
Okay, we'll put it.
Okay. So there's the magnetic force that I've created. What shape is this thing going in? It's a circle. So what kind of force is this? It's a centripetal force. It's a circular force. I can use that. Let's see if I can make this work. Shrink this picture down. Move it over here. So I know that the force here is equal to Q times V cross B. If I want to get just the magnitude, how do I get just the magnitude of this force? QVB cross product V cross B is V times B times sine of the angle between the two. What's the sine of the angle between V and B?
1.
It's 1, because it's 90 degrees. So the force that I'm acting with here is just QVB. What kind of force is this? It's a centripetal force. What's the equation for centripetal force?
Oh, F equals QB over 2. No, just kidding. Don't listen to me.
Okay. Hear that, YouTube? Don't listen to her. You probably can't hear her anyways. MV squared over R.
Yes, listen to Quinn.
That is the equation for centripetal force. So I can take this magnetic force and I can set it equal to the general centripetal force equation. QVB equals M times V squared over R. And then I can solve for various things in this. I can use this for various applications. In a mass spectrometer, something that you might use in labs, in chemistry labs, to figure out chemical identities. How many of you ever used a mass spectrometer? And have you learned about them?
Yes.
No,
Now you're going to.
In ortho.
And you're going to do a problem about them and how they work.
Good.
You can use them to find the mass. Right? So I can get all these variables. What things can I measure about quantity? I can measure how big a charge is. I can measure how fast something's going. I can measure a magnetic field, how big a magnetic field that I put something in. I can measure, again, how fast something's going, and I can measure an arced path that I get. So I can calculate the mass. That's one application for a mass spectrometer. Maybe you know the mass of what you're sending in, so you can find out the charge of what you're sending into this. This is all physics. The mass spectrometer you literally have used, some of you raised your hands, it was using this kind of stuff. You just didn't learn it. Yeah. Gross? That's not gross. That's sexy. Okay. So what your book, and I think what the example does, they use all this to calculate what R is, how big this path is, how big the radius is that this thing's traveling. So how would I do that? How do I find R from all of this? I do some algebra. Right. I bring my R to the left side and my QVB down to the bottom. So I can do that. R over then MV squared divided by Q times V times B. One of those V's cancels out, and I get the R is MV over QB. So inside of this thing, I know that the radius that this thing is going to follow in this magnetic field path is M times V divided by Q times B. And I can adjust the path that it follows by changing the magnetic field. I can change the velocity, how fast I shoot this thing into the magnetic field, anything I want. All using physics, pretty simple physics. Okay? And where we usually use this in a mass spectrometer is in combination with something called a velocity selector. So velocity selector is what we're going to talk about next. Any questions on this? So this was all just a rehash of the first, 10, 15 minutes of the lecture. So what we want to do is we actually want to get a particle into a magnetic field so that it will travel in this kind of arced path. And the way we do that, the way we control velocities of particles is with velocity selectors. So let's do an example of those. So this is going to be number 16 from the book. There's lots of text that goes along with problem number 16. We don't really need to know the text. You can read it yourselves on your own time. But what we have is a particle that's traveling between two plates. We have a positive plate and a negative plate. So two parallel plates. If I have two parallel plates, what ends up being created in between these? Force. And what creates that force? Field. So where does the field go? Towards the negative. What about the positive?
The positive goes towards the negative.
Positive goes towards negative. So we have a field that goes away from the positive and towards the negative. So I create an electric field that's going to go this way. Constant electric field. And now I'm going to take a charge and I'm going to shoot a charge into it. What color charge do you want? Green? We're going to do a green charge then. We're going to take a green charge. Positive or negative charge? We're going to do a positive charge. And we're going to shoot it into this field. I take that positive charge. I shoot it into the field. Where is it going to go? Is it going to go straight through? Is it going to go up? Is it going to go down? It's going to go down. Why is it going to go down? Positive charge attracted to the negative. So it feels that electrical force. It's going to kind of arc down. Because it feels an electric force. Fe. How big is Fe? Fe is equal to the charge times the electric field that you're in. Now I want to take this thing and I want to shoot it into a mass spectrometer, and my mass spectrometer has a magnetic field over here. So I want this to get into the mass spectrometer right here at this point. So I want this charge to travel straight through completely undeflected. Right now it's feeling an electric force. I need to apply another force that'll counteract the Fe so that the charge just goes straight through. Yep. So I can put a magnetic field inside of this. We'll make the magnetic field blue. So I turn on a magnetic field, constant magnetic field. What direction is the magnetic field going to pull this? I can figure it out with the right-hand rule. What direction am I moving? Moving to the right, do this. So take my fingers and I put it to the right. What direction is my magnetic field as I've drawn it? Going into the board. So I rotate my hand so I can bend my fingers and they're going into the board. What direction is my thumb pointing? Up. So I have a magnetic force that's going up. Okay. What is the magnitude of that magnetic force? How big is the force acting on a charged particle that's moving with a velocity v and a magnetic field b? QVB. If I want this to pass through undeflected, I want the electric force to balance with the magnetic force. I want those to be equal. So I'm going to do Fe equals Fb. So QE, I just plug in my equation. Right, plug that in for Fe. It's QE equals Fb. Plug in QVB. Does my charge matter? What happens to the charge? Cancels out, goes away. Who cares? We can use whatever charges we want. This is why a mass spectrometer can work for various different solutions that you might put into it. We don't care about the charge. Velocity then ends up being E divided by B. And that was the whole purpose of this problem, to prove that the velocity is E over B for a particle to pass through a velocity selector undeflected. How many points would this be worth on an exam? As it is here, this is maybe 5 points. On an exam, to make it a full problem, maybe I don't give you the direction for the magnetic field. You have to figure that out. And then I make the charge negative. And then I combine it with problem number 17, which asks you to actually calculate something. Or maybe I give it like the sheets that you have in front of you. Okay? Any questions on number 16? Nothing on 16? Okay, let's do number 25. This should be fun because I have to draw in 3D. So number 25, we have this box. X, Z direction, and Y direction. That's not horrible.
No.
3D box. You're lopsided. So I have a wonderful lopsided box. And what I'm doing in this problem is I'm taking some currents. I'm going to make some currents move along the surfaces of this box. So I take a current comes in the X direction and goes along here, one segment, and then it goes up the side of this cube, and then to the front of this cube, and it kind of goes to the back of the cube, and it goes down, and then it goes away. So I have current here, current up here, current over here, current here, current here, and current here. And then I take a magnetic field and I set up a magnetic field that's going entirely in the X direction. And they ask me to find what is the magnetic force that this thing experiences. So what is the general equation for the magnetic force acting on a current moving in a magnetic field? There's a general equation for it. It's similar to QVB. I times L times B times sine of theta. Nah, F equals Bill. Sine theta. I've never noticed that one. Usually I catch them.
Oh. I had a full conversation with Kathy.
Wow.
That's how I refer to it.
F equals ILB sine theta, or BIL. The problem with BIL is the order does matter for the cross product. Okay, so I, whatever the current is, times L, whatever the length of the wire is, times B, whatever the size of the magnetic field is, times the sine of theta, which is the angle between where the current's going and where the magnetic field goes. How many different wire segments do I have inside of this magnetic field? Let me label them. That one's A, this one going up is B, then C, then D, then E, then F. Holy crap, that's a lot of segments. So I have to calculate this 6 times. But I can make it easier, it becomes a lot easier. I look at the direction of the magnetic field. What axis is the magnetic field going along? What is it parallel to?
X-axis.
The x-axis. If I have anything else going along the x-axis, then it's going to cancel out and give me 0. Because then the angle is 0, sine of theta is 0, and the force would be non-existent. So anything that's traveling along the x-axis gives me 0 force. Anything that goes in the same direction as your magnetic field. This was true on the quiz for a lot of questions that people miss. Anytime something's going parallel or anti-parallel, the magnetic force is going to cancel out. Okay, So I'm going to call this my Christmas cube. Looks Christmas. Which segments of those are going to be 0? ACF. AC and F all give me 0 force. So I don't care about any of those. Who cares about A? Who cares about C? Who cares about F? They all cancel out. So now I have to calculate what the forces are on the other segments that I have left. Let's do FB. IL cross B. So I have to do this cross product. They give us the current. The current is 25 amps. They gave us the length of the wire. The length of the wire is 0.25. They gave us the magnetic field is 2. So I can multiply all those out and I get 12.5. So that's the magnitude. But then I still have to do this cross product for segment B. So what direction is the current going? Current is going in the Y direction according to the way this is drawn. So that would be up, right? And then the X direction, the way this is drawn, the way they gave it in the book, they gave us X is actually going out of the board. Normally that's Z, but that's what direction, right? If I bend my fingers, my thumb is now pointing that direction, which is opposite to the positive. So what is that? So that's going to be negative K. So I have, let's maybe write this out. I'm going up, which is, what direction is that? Well, it's Y direction, which in unit vectors is J hat. And I cross it into coming out of the board. And coming out of the board for this particular diagram is X, which would be, X is I. Okay, and J cross I does give me negative K. So I got 12.5 in the negative K hat direction for FB. What else do we have to calculate? That's not the only force. I still have 2 other segments. What other segments? E and D. So let's do FD. ILB, still the same numbers. So I get 12.5. What changes is the direction. ILB for segment D. My fingers are going in that direction. That's opposite to the Z, so that's negative Z, which would be what direction? Negative K hat. So I'm going in negative K hat. What direction is my magnetic field going? It's coming out, positive X. So that's negative K hat cross I hat. And what does that give me? This way. Bend my fingers, thumbs pointing down. I'm pointing down. Negative J hat. Okay. CD, let's do E. Same magnitude, 12.5. I have the same current, same length of the wire, same magnetic field. Now I'm going down, so my fingers have to point down. I bend my fingers, they come out. What direction is my thumb going? On this picture. Z, which would be K hat. Positive because it's coming out. So I have FB is negative 12.5 K hat. FE is 12.5 K hat. What happens to those two? They cancel out. So my final answer is FD equals 12.5 in the negative J hat direction. This one's tricky because it's in 3D. It's like the box. You have to sit down and work it out. Think about it a bit. Shortcut. You know, shortcut? Here I have a current going up. I have a current going down, they're going to cancel each other out. Right? So we can use the physics that we know to know those are going to cancel out. And D is the only one I actually have to calculate.
They're anti-parallel.
They're anti-parallel with each other, so they'll cancel out. Anytime you have two that are anti-parallel, they'll cancel out. You have anytime that the current is parallel to the magnetic field, 0. Okay? What if I added another segment to this? What if I said instead of going down, then up, then down, then over, then down, it went over this way and then out? What would that do? What'd you say?
Oh, wait, no, never mind. You'd only have to find that segment right there, right?
I liked your answer. What was your first answer?
But they all cancel out.
They all cancel out. Parallel, oh, there's an anti-parallel part, gets rid of it. Parallel, up, anti-parallel with that, gets rid of it.
Which one?
Total force. So if I add in this segment,
Oh.
I'm going right here, I'm going left here, cancel out, 0 force. And then how easy is that for me to grade?
For us to do.
And how easy for you to do?
This should be 20.
If we figure that out,
Super easy. By the time you have the exam, all of you are going to forget this.
Yep.
And you're going to do like 10 pages of algebra to get the answer, and I just won't look at any of it. Because it's just 0. Super easy. Okay. Any preguntas on this one? No preguntas? Bueno. Bien. No sé. Okay.